Hi, now we will solve the second problem of the 2024 International Mathematical Olympiad. This problem also doesn't require heavy calculations and is about patterns and logical reasoning. We are given two positive integers a and b, and we form two expressions a to the power n plus b and b to the power n plus a. As n increases, these numbers grow very rapidly. The interesting question is not how much they grow, but what happens to their greatest common divisor. Does it continue to change indefinitely, or does it eventually settle at a constant value? This problem asks us to find all pairs of A and B where this surprising stability can occur. That's the idea we will explore. So let A and B be positive integers. Suppose there exist positive integers g and n such that for all n is greater than or equal to n, the greatest common divisor GCD of a to the power n plus b and b to the power n plus a equals g. Find all such pairs a and b. Alright, everyone, let's slow down and carefully understand what this problem is really asking. We are given two positive integers a and b. For each value of n, we form two numbers a sub n equals a to the power n plus b. B sub n equals b to the power n plus a. Then we take their greatest common divisor, meaning the greatest common divisor of a sub n and b sub n. Now here's the key idea. Is n gets larger, these numbers grow extremely fast. So normally we would expect their common divisors to keep changing. But the problem says something very special. After some point, once n is big enough, the GCD becomes a fixed constant and never changes again. That is not normal behavior. So the real question is, for which values of a and b can this possibly happen? Now, can it happen once, but can it eventually stay the same forever? This is a pure reasoning problem. We are not here to calculate GCDs. We are here to understand what kind of numbers could force this stability. And as we will see, this condition is extremely restrictive. Alright, now that we understand the goal, let's begin the reasoning. Okay, before we go any further, let's make sure everyone is completely comfortable with what the greatest common divisor or GCD actually means. On the screen, we have a simple example, the greatest common divisor of 16 and 12. First, let's look at all divisors of 16. A divisor is a number that divides evenly with no remainder. So for 16, the divisors are 1, 2, 4, 8, and 16, you know. That's why you see those numbers highlighted in the top row. For example, 2 vertical line 16 is read as 2 divides 16. 4 vertical line 16 is read as 4 divides 16. The other example, 8 vertical line 16 is read as 8 divides 16. Now we do the same thing for 12. The divisor of 12 are 1, 2, 3, 4, 6 and 12. Again, 2 vertical line 12 means 2 divides 12. 3 vertical line 12 means 3 divides 12, etc. Next, we look at the numbers that appear in both lists. These are called the common divisors. From the table, we can see that the common divisors of 16 and 12 are 1, 2, and 4. Finally, we choose the largest of these common divisors. That number is 4. So we conclude the greatest common divisors of 16 and 12 is equal to 4. Now, here is the most important sentence on this slide. The one written in red. In our problem, we are not computing the GCD. We are asking whether it eventually stops changing. This example is only here to remind us what a GCD is. In the actual problem, we won't be listing divisors or calculating values like this. Instead, we are asking a deeper question. Can the greatest common divisors of two growing expressions eventually become fixed and stay the same forever? That idea, not the calculation, is what drives the entire problem. Alright, now that the concept of GCD is clear, we are ready to move on. This slide is about understanding the question, not solving it. Look at the big word in the middle of the slide. Imagine, only imagine. That word is doing a lot of work for us. What we are about to see is hypothetical example. We are not claiming that such numbers a and b actually exist. We are saying suppose this happens. So imagine the following situation. When n is equal to 3, the greatest common divisor of a to the power n plus b and b to the power n plus a is 12. When n is 4, the GCD becomes 36. When n is equal to 5, the GCD becomes 180. And then something interesting happens for n. If n is equal to 6, the GCD is still 180. For n is equal to 7, the GCD is still 180. So after n is equal to 5, the GCD stops changing. That is exactly the behavior the problem is talking about. The key idea is not the numbers 12, 36 or 180. Those numbers are completely made up. The key idea is the pattern. The GCD may change at first, but after some point it becomes constant and stays that way. That point is what the problem calls n. So when the problem asks, find all such pairs A and B, is really asking, can this kind of stabilization actually happen? And if it can, for which values of A and B? In the rest of the solution, we are going to test whether this imagined behavior is even possible. Alright, now that we are clear on the goal. Yes, this slide is extremely important. In fact, everything we do next is based on one single rule and nothing else. So, if you understand this rule, you understand the entire solution. Here is the rule states clearly. If a number g divides x and g divides y, then g also divides any integer linear combination of x and y. On the screen, this is written as g divides x minus k times y for any integer k. Now, let's slow that down and make it concrete. First, a very simple consequence. If g divides x, then g divides k times x. True? For any integer k. That just means if g divides a number, it also divides any multiple of that number. Nothing fancy. Simple. Second, here is the key idea we will use again and again. If g divides x and y divides y, then g also divides x minus y. True? Then this is what we call the multiply subtract rule. This is what we call the multiply subtract rule. And the reasons is so powerful is this. It lets us take large, complicated expressions and turn them into smaller, simpler ones by multiplying and subtracting in a smart way. That's exactly how we are going to eliminate exponents later. One last thing to emphasize, we are not introducing new theorems. We are not using advanced number theory. Everything in the solutions comes from this one basic idea. If g divides two numbers, it also divides their difference and their multiples. So keep this rule in mind because from this point on, every step of argument is just a careful application of it. Okay, now we officially start the solution and the very first thing we ask is this. What does the assumption of a constant GCD actually give us? Let's read it carefully. We are assuming that there exists a number g and a number n, such that for every n greater than or equal to n, the GCD is equal to g. So in symbols, this means g divides a to the power n plus b, and g divides b to the power n plus a. And this is true for every small n greater than or equal to big N. We have to separate big and small n. In other words, think of big N as a fixed cutoff, okay? And small n as a variable that runs past it. Now let's slow down and take advantage of that. If something is true for every n greater than or equal to n, big N, then it's certainly true for specific choices of small n. So first, take n equals n when small n is equal to big N. Remember, small n, big N, lowercase n moves, uppercase n stays fixed. Okay, we get g divides a to the power big N plus B. And G divides B to the power big N plus A. That's our first pair of numbers that G divides. But we don't stop there, because the statement also holds for n is equal to big N plus 1. So when small n is equal to big N plus 1, we also have G divides A to the power N plus 1 plus B, and G divides B to the power N plus 1 plus A. That gives us another pair of numbers that are divisible by G. And this is the key point of step 1. From the constant GCD assumption, we now know that G divides 4 different expressions: A to the power N plus B, big N, B to the power big N plus A to the power N plus 1 plus B to the power N plus 1 plus A. We haven't done any algebra yet. We've just carefully unpacked what the assumption really means. And this is exactly what we need before applying the multiply subtract rule in the next step. Alright, now that we know what G divides, we are ready to use this information. Alright, now we move on to solution step 2. Our goal in this step is very simple. We wanna eliminate the exponents. And we are going to do that using the multiply subtract rule we just discussed. Let's start with the A side. From step 1, we know that G divides both of the following numbers: A to the power N plus 1 plus B and A to the power and A to the power plus B. Of course, these are big N. Both of these are divisible by G. Now, here's the key idea. We want to make the powers match, so we can subtract them. Notice that A multiplied by A to the power N equals A to the power N plus 1. So we take the second expression, A to the power N plus B, and multiply it by A. That gives us A times open parenthesis A to the power N plus B close parenthesis. Since G divides A to the power N plus B, it must also divide any multiple of it. So we can say G divides A times A to the power N plus B. Now comes the subtract step. We subtract the two expressions A to the power N plus 1 plus B minus A times open parenthesis A to the power N plus B close parenthesis. Let's expand the second term. A times open parenthesis is open parenthesis A to the power N plus B close parenthesis equals A to the power N plus 1 plus AB. Now subtract A to the power N plus 1 plus B minus open parenthesis A to the power N plus 1 plus AB close parenthesis. The A to the power N plus 1 terms cancel out because of negative and positive states, and we are left with b minus a times b. Now factor out b times open parenthesis 1 minus a close parenthesis. So our conclusion is G divides B times open parenthesis 1 minus a close parenthesis. And since divisibility doesn't care about signs, this is equivalent to G divides B times open parenthesis a minus 1 close parenthesis. That's the result of the A side. We started with two expressions involving high powers, and using multiply subtract, we reduced everything to a simple linear expression. This is exactly why this method is so powerful. In the next step, we will repeat the same argument on the B side and then combine the results. Now we do the exact same thing on the other side. This step is completely symmetric. So nothing new is happening conceptually. From step 1, we know that G divides both of these expressions b to the power n plus 1 plus a and b to the power n plus a. Since both are divisible by G, we can again use multiply subtract rule. Notice that b times b to the power n equals b to the power n plus 1. So we multiply the second expression, b to the power n plus a. That gives us b times b to the power n plus a, because G divides b to the power n plus a, it must also divide b times that expression, isn't it? So we can write G divides b times open parenthesis b to the power n plus a close parenthesis. Now we subtract b to the power n plus 1 plus a minus b times open parenthesis b to the power n plus a close parenthesis. Let's expand the second term. B times open parenthesis b to the power n plus a close parenthesis equals b to the power n plus 1 plus ab. Okay, now subtract b to the power n plus 1 plus a minus b to the power n plus 1 plus ab. The b to the power n plus 1 terms cancel, and we are left with a minus ab. Factor out a again, a times open parenthesis 1 minus b close parenthesis. So our conclusion from the B side is G divides a times open parenthesis 1 minus b close parenthesis. And again, since divisibility does not care about signs, this is equivalent to G divides a times open parenthesis b minus 1 close parenthesis. At this point, we have eliminated the exponents on both sides. Next, we will combine the results from the A side and B side and see what they force G to divide. Okay, all right. Let's stop here for a moment. This slide is extremely important because everything that comes next depends on it. After all the multiply subtract steps and after eliminating the exponents on both sides, we are left with just two simple facts. Here they are. G divides B times A minus 1 and divides uh, G divides A times B minus 1. That's it. No powers, no large expressions, just these two small products. Now, why is this so important? Why? Because this tells us something very strong about G. Every prime number that divides G must also divide both of these expressions. So instead of worrying about huge numbers like a to the power n plus b, we only need to think about how prime divisors of G interact with only a, only b, a minus 1, and b minus 1. That is a massive simplification. We've gone from exponentials to linear expressions. And from here on, the argument becomes much more controlled. So keep this slide in mind. These two divisibility statements are the key constraints that drive the rest of the solution. Alright, now let's see what these conditions actually force G to look like. So now we take the next logical step. Up to this point, we've learned something important about G. Now we wanna zoom in even further. So here's what we do. We pick a prime number p such that p divides g. In other words, p is a prime divisor of g. Now remember what that means. If p divides g and g divides certain expressions, then p must divide those expressions as well. So from the original assumption, we immediately get for every n greater than or equal to n, p divides a to the power n plus b and p divides b to the power n plus a. But we also have information from step 2. From eliminating the exponents, we found that p divides b times a minus 1 and p divides a times b minus 1. So now everything is expressed in terms of small, simple products. This is the key idea of step 3. We've reduced the entire problem to understanding how a prime number p can divide both of these expressions at the same time. In the next step, we will analyze what this forces P to do, and we will see the possibilities become extremely limited. Now we move to a critical step. At this point, we are going to assume something and see where it leads us. So assume P does not divide A. Our goal is to show that this assumption leads to a contradiction. Since P divides a to the power n plus b, we can rewrite that statement is using remainders. If P divides a to the power n plus b, then that means a to the power n is congruent to minus b module p. And this holds for all sufficiently large n. Now here's the key move. Because the statement holds for all large n, it must hold for n, also for n plus 1. So we can write a to the power n congruent to minus bn, and a to the power n plus 1 is congruent to minus b module p. But we also know how a to the power n plus 1 is related to a to the power n. We have a to the power n plus 1 equals a times a to the power n. And substitute the congruence for a to the power n. A to the power n plus 1 is congruent to a times negative b, which equals negative ab module p. Now compare two expressions for a to the power n plus 1. We have minus ab is congruent to minus b module p. Subtract minus b from both sides. B times a minus 1 is congruent to 0 module p. Okay? And this is exactly what we found earlier from the multiply subtract step. So our assumption that p does not divide a forces. P divides b times a minus 1. This agreement is important. It tells us our logical is consistent. In the next step, we will push this condition further and see that it eventually leads to a contradiction. Alright, now we continue pushing our assumption. We already assume that P does not divide A, and we reach the condition B times A minus 1 is congruent to 0 module P. Now suppose P does not divide B. If P does not divide B, then the only way B times A minus 1 is congruent to 0 module P can be true is if A minus 1 is congruent to 0 module P. That means A is congruent to 1 module P. Now we substitute this into expressions. A to the power n plus b is congruent to 0 module p, since a to the power a congruent to 1 module p. A to the power n is congruent to 1 module p. So we get 1 plus b is congruent to 0 module p, which means b is congruent to minus 1 module b. Now look at the other expressions. B to the power n plus a is congruent to 0 module p. Substitute a is congruent to 1 module p. B to the power n plus 1 is congruent to 0 module p, which gives b to the power n is congruent to minus 1 mod p. But now recall b is congruent to minus 1 module p. So if n is odd, b to the power n is congruent to -1 mod p. If n is even, b to the power n is congruent to +1 mod p. The contradiction subject is but the original condition must hold for all n greater than or equal to n, which means both odd and even values of n occur. So b to the power n would have to be +1 and -1 for module p at the same time. That is impossible. So we reach a contradiction. This contradiction shows a prime divisor P of G cannot be unrelated to both A and B. In other words, our assumption that P does not divide A and P does not divide B cannot be true. Okay. Alright, after all that reasoning, we are finally ready to test a concrete candidate. Now we test A and B equals 1, 1. Let's substitute this into our expressions. First, a to the power n plus b is equal to 1 to the power n plus 1. But 1 to the power n is equal to 1 for every n. So 1 to the power n plus 1 equals 2. Now check the other expression. B to the power n plus a equals 1 to the power n plus 1 equals 2. So both expressions are equal to 2. Now take their greatest common divisor, GCD 2, 2 is equal to 2. And here's the key point. This value G equals to is constant for all n. It never changes. So we can confidently say 1 and 1, the pair 1, 1 definitely works. Alright, now we are ready to finish the argument. We've shown that the pair 1, 1 works. Now we explain why no other pair can work. Start with the assumption. Suppose A and B, A, B is not equal to 1, 1. That means at least one of the numbers A or B is greater than 1. What happens to the expressions? Look at the two expressions, A to the power n plus B and B to the power n plus A. When A greater than 1 or B greater than 1, these expressions grow very rapidly as n increases. As numbers grow, their prime factorizations change. In particular, when n changes, and especially when n switches between odd and even, the prime factors of A to the power n plus B and B to the power n plus A also change. This means new prime numbers are eventually forced to appear in both expressions. Why is that a problem? Why is that a problem? Because we are assuming that the greatest common divisor GCD of A to the power n plus B and b to the power n plus a equals g is constant for all large n. But a GCD that stays constant cannot keep absorbing new prime factors. Once a new prime appears in both expressions, the GCD would have to change. And what violates the assumption? In step 4, we learned earlier, in step 4, we proved that any attempt to keep the same prime divisors leads to a contradiction once we consider odd and even values of n. Parity odd versus even forces the behavior to change. So the only way to avoid all contradictions is for the expressions to behave trivially. And that happens only when A and B are equal to 1. Because 1 to the power n equals 1 for all n. The expressions never change and the GCD stays constant forever. The only solution is a comma b equals 1 comma 1. The condition is so strong that it forces the numbers to stop changing, and only one pair can do that. Okay, we've reached the end. Here's the final answer. A and B is 1 and 1. In this case, the constant value of the greatest common divisor is 2. And that's it. This pair doesn't work just once. It works for every value of n. So the GCD becomes 2 and stays 2 forever. Let's take 30 seconds and summarize the entire solution. First, we carefully understand what the problem was asking. We were not computing a GCD, we were asking whether it could eventually stop changing. Next, we used one basic idea. If a number divides two expressions, it also divides their differences and multiples. Using that multiply subtract rule, we eliminate the exponents and reduced everything to simple linear expressions. Then we focused on a single prime divisor of the GCD and asked what must this prime divide. From there we tested what happens if that prime does not divide A or B, and we showed that this leads to contradictions, especially when we consider odd and even values of n. Finally, we tested the only remaining candidate 1, 1 and verified that it truly works. And we explained why no other pair can survive all of those constraints. This problem is a great example of how a very strong condition forces a very small set of possibilities. When something must hold for all large n, mathematics becomes extremely rigid. Alright, that's the complete solution. Thanks for working through it carefully. We will stop here and we will meet again in the next solution. Until then, keep thinking mathematically. Thank you very much. Bye bye.